Now let's start looking at the map pattern here. We're going to introduce the map pattern by means of the Saxby operation. The Saxby is an operation when you scale a vector. So you have the vector x, you scale it by a factor of a scalar factor a. So each element of vector a is scaled by the factor a. Then you add it to a vector y, and you store the result in the same vector y. So y is used both for input and output. So Saxby is a single precision floating point. The same operation on double precision is called Daxby. Unfortunately, this is an operation which is low arithmetic intensity. Arithmetic intensity is a measure of how much work there is to do on each data element. So it's with a low arithmetic intensity, we have little arithmetic work compared to the amount of data consumed and produced. So we do only for each data element, we do a floating point, two floating point operations. We do the multiplication and we do the addition. But there are 8 bytes read, 4 for the x element, 4 for the a, and then 4 for the x, 4 for y. The a is not read, it's held in a register typically, and then 4 bytes written. So 4x, 4y, and 4y stored. Low arithmetic intensity means that it's difficult to get any speed up, but it's a useful illustration for the map pattern anyway. So the map pattern applies a function f, to every element of a collection of data items. And this, in this case, and which is always the case in the map pattern, is the same function. It's an elemental function. There are no side effects. This kind of pattern results in programs that are called embarrassingly parallel because there is no communication. So between, if you could do this totally in parallel and there is no communication between them. But it's often combined with collective patterns like reduce and other kind of collective patterns which do create some communication. But the map pattern alone does not contain any communication between the parallel activities. Let's go back to C++ 11 thread programming. Again, mention that you need to specify the standard minus std equals C++ 11. It's a good practice also to introduce optimization. So minus O or even minus O3 is a standard practice to use, and minus LP thread to get access to the threads of the operating system. Put this in the top of your program, declare a thread this way. The T is a thread handle. Instantiate the thread with the function foo and arguments A1 and A2. You can join with that thread later on, and you can declare a mutex this way. You lock and unlock and so on for critical sections. This shouldn't be new to you. So a naive approach of implementing the map pattern with explicit threading in C++ 11 is to create a thread for each element in the array. This is a bad idea. Threads take really long time to create and join. I'm not talking about a couple of cycles. I'm not talking about hundreds or thousands of cycles. I'm talking about millions of clock cycles. And also, operating systems have limitations on the number of threads. So on Linux, normal Linux distributions, it's typically around 1 million threads, which is the sort of the limit. And then the operating system will need to schedule these threads and so on. Your performance will go down the drain. It's really, really, really a bad idea. But if you still want to do it, it's simple. You have the Saxby function here. It takes a floating point number, the scaling factor. It takes a pointer to the X array. It takes a pointer to the Y array. And it takes a thread identity. And then there is no for loop any longer here. You will just do the scaling and you will do the addition and then storing here. And then we create the thread by doing a for loop out here with n elements. Sorry. With n elements here, and you declare one thread per element, and then you wait for the threads. Again, this is a really bad thing, but this code actually looks very similar to what you would write when you write, for instance, a CUDA kernel for executing on a GPU. In GPUs, this is the style of programming you would do. So similar to CUDA kernel here. But on a multi-core processor, this is bad. Instead, you need to do some kind of work sharing or work distribution. First of all, which is good practice, you would like to create at most one thread per core in the machine or per core that you would like to use. If you oversubscribe the machine with more threads than you have cores, then the operating system will take turns doing load context switching. And if you've divided the work among the threads in such a way that they would finish about the same time, if you then with multiple threads, more threads than you have cores, you would create, in fact, load imbalance, even though you carefully divided the work so that each thread would have the same amount of work. So one thread per core maximum. So in this example, which is similar to what we saw earlier in the course, we create a number of threads with a for loop here, put each thread in an array with thread handles. The thread function uses the number of, as arguments, the number of elements in the array, the scaling factor pointed to the X array, pointed to the Y array, the number of threads that take part here, and the local thread identity. And this thread ID is equal to the for loop index variable in this case. So by passing these arguments to the thread, you pass them to the thread instantiation function, you pass them to the thread here. And we divide the work to the different threads in a way so that we have the X array, and we have the Y array, and we say that if we have 4 threads, for instance, thread 0 performs these data elements, thread 1 these, thread 2 these, and thread 3 these. And the way we do that is by taking the thread identity, multiplying by the number of items divided by the number of threads. So that will give a starting index here, and then we do a similar kind of thing for the end index, which would give you this one, or we take the minimum of the total number of items here, so that we can take care of when n is not evenly divisible by the number of threads. And then we do the for loop here, starting from the start index and finishing by the end index, and we're done. So this is a static, even work distribution to the different threads. Work distribution is done by specifying the start and the ending indices here. If there would be load imbalance, so now it's not a big deal for this code here, because the work done is exactly the same for each iteration. But there could be a load imbalance, and then you might want to think about doing this in a different way. We'll come to that later on.